If you're a developer, you know the feeling, right? You start a new project, the code is just beautiful, it's clean. But then, over time, it just starts to decay. It gets messy, fragile, and it becomes a total nightmare to change. Well, today, we're diving into the toolkit designed to prevent exactly that, the 5 solid principles.
So why does this happen? Well, there's this thing called software entropy. It's like, without a solid set of rules to guide you, every new feature, every little bug fix, it just adds a tiny bit of chaos. Before you know it, all your components are tangled together, and making one small change over here causes a total cascade of failures somewhere else. Your code becomes rigid, fragile, and just impossible to maintain. So, how do we fight back?
The answer is to build on a solid foundation. And look, these aren't just some abstract academic theories. They are 5 battle-tested design principles popularized by the one and only Robert C. Martin. Think of them as your guide for writing professional, resilient, and really adaptable code.
Okay, so here's our game plan for today. First, we'll get the big picture of what solid even is. Then, we are going to tackle each of the 5 principles, one by one, from single responsibility all the way to dependency inversion. And you're going to want to stick around to the end, because I've got a really handy cheat sheet that's going to help you spot these patterns in your own code.
So what is SOLID exactly? Well, it's an acronym. Each letter stands for a core principle of object-oriented design. You should think of it less like a set of strict laws and more like a set of guidelines that help you arrange your code in a way that's logical, clean, and, built to last.
And why should you even care? Well, honestly, because following these principles just makes your life as the developer so much easier. Your code becomes way simpler to understand, it's less likely to break when you add new stuff, and it's a whole lot easier to test. Basically, SOLID helps you build systems that don't fight you every step of the way.
Okay, let's dive right in with the S in SOLID, the single responsibility principle. This one is probably the easiest one to get, but it is incredibly powerful. The motto is simple: do one thing and do it well.
So the formal definition says a class should have only one reason to change. But what that really means is it should have only one job. Just one. Think about it with the chef analogy. The chef's job is to cook. That's it. If the chef also had to wash the dishes and wait tables, everything would grind to a halt. It's the same with your code. If one class is handling business logic, database stuff, and sending emails, any change to any of those things forces you to mess with the whole class. It becomes a tangled mess.
And here is a perfect example. On the left, you've got this one bloated order class just trying to do everything. If you need to change how the database works, or how emails are formatted, or even the calculation logic, you risk breaking the whole thing. But now look at the solution on the right. Ah, so much cleaner. The order class just handles order logic. The order repository just saves stuff, and the email service just sends emails. Each piece has one job, which makes it super simple to change and so much easier to test. Let's move on to the O, which builds on this idea. This is the open/closed principle. The goal here is kind of the holy grail in software. How can we add new features without ever touching old, working, and already tested code?
The principle says that our code should be open for extension, which means we can easily add new behaviors. But it should also be closed for modification, meaning we shouldn't have to go back and change the original source code to do it. Now, I know that sounds like a total contradiction, but it's actually made possible through the magic of abstraction.
Okay, on the left, this is a classic code smell. A giant endless chain of if-else statements. Every time you want to add a new payment type, say Bitcoin, you have to crack open this core class and add more logic. That's risky. The solution is abstraction. By using an interface, which is kind of like a contract, our payment processor stops caring about how a payment is made, it just cares that it can call a process method. Now you can add a Bitcoin payment class, an Apple Pay payment class, you can add new payment types all day long, and that original processor code never needs to be touched. That's the magic. Open to new features, closed for modification.
All right, next up, we've got the L for the Liskov Substitution Principle. I know, this one sounds a little academic, maybe even a bit scary, but its core idea is actually super simple and really important. No surprises. It's all about making sure our abstractions are trustworthy.
So what this really means is that if you have a piece of code that works with a parent class, you should be able to swap in any of its child classes, and everything should just work. No weird side effects, no hidden bugs. The child class has to honor the contract of the parent. Simple as that. So let's look at the classic example that trips almost everybody up. In geometry, it makes perfect sense that a square is a special kind of rectangle, right? So we write code like this. We make a new square, But we tell our program, hey, just treat this like a rectangle. Then we set the width to 5 and the height to 10. Seems simple. So what do you think the area is going to be?
You'd expect 5 times 10, so 50, right? Nope, the area is 100. So what just happened? Well, our square class, in trying to be a good square, secretly changed the width to 10 when we set the height to 10, because a square's sides have to be equal. It completely broke the rules of how a rectangle is supposed to behave. That is a Liskov substitution violation, a really nasty hidden bug waiting to happen.
The real fix here is to rethink the relationship entirely. Just because two things are related in math doesn't mean they should be related through inheritance in our code. So instead of forcing that is a relationship, we create a common interface, like shape. Now both rectangle and square can implement shape, but neither one can mess with the other's internal rules. They're independent, but they share a common type. And no more surprises.
All right, let's wrap this up with our final two principles, I and D. We're going to tackle them together because they're both about one critical goal: creating clean boundaries between different parts of your code so everything isn't one big tangled mess.
These analogies are just a great way to remember these. For interface segregation, or ISP, think of a Swiss Army knife. It's great, but if all you need is a screwdriver, you shouldn't be forced to carry around the whole thing. It's the same with code. Your classes shouldn't have to depend on methods they don't even use. And for dependency inversion, or DIP, think about your TV remote. It doesn't care if you put in Duracell or Energizer batteries, it just depends on the abstract idea of a AA battery. Your high-level code should work just like that, depending on abstractions, not on concrete details.
So let's see how we can fix these. For ISP, imagine you've got a single, fat worker interface. If a robot class has to use it, it might be forced to have an eat method, which is, well, just weird. The fix is to split that up into smaller, more focused interfaces like workable and eatable. And for DIP, the problem is having your notification class directly tied to something specific, like an email service. The fix is to make it depend on a general message service interface instead. That way, you can plug in an email service, an SMS service, whatever you want later, without ever touching the original notification class.
Okay, wow, we have covered a lot of ground really quickly. So to bring this all together, let's look at a quick cheat sheet you can use to start spotting these issues in your own code.
And here it is. This is how you spot these problems in the wild. If you see a class that's doing way too much stuff, that's a single responsibility problem. You see a giant if-else block checking for different types, you probably need the open-close principle. A child class that throws not supported errors, that's a classic Liskov violation. A class that has a bunch of empty methods, that's an interface segregation issue. And if you see a class creating its own dependencies with the new keyword, that's a huge red flag for dependency inversion.
Look, it's true. Applying these principles can feel like a little more work up front. But I promise you, that small initial investment in design pays off enormously down the road. It gives you code that's flexible and, honestly, a joy to work with, not a nightmare to maintain.
And that's our deep dive into the solid principles. They're not just a set of rules, they're a mindset for building professional, high-quality software. So my final question to you is this: which one of these are you going to try and apply to your code tomorrow? Let me know what you think. And that's the explainer.